Thank you. So can you hear me well? Yeah. So I'm Romain Dupuis. So today I'm going to talk about simulations. Yes, do you hear? Yeah, okay. So I'm going to talk about simulations, and that might be a bit different compared to what we've seen before. And I'm also showing some stuff that is about nanoporous carbon supercapacitors. So this is work I've been doing with Katerina and Roland alongside the last years at MIT and now at LMGC in Montpellier in France. So sorry, I have to accept. Yeah. Yes, so the idea is that, okay, we try to understand what's happening from the molecular level. So I'm going to do a small introduction of molecular dynamics, but more to try to understand what are our challenges, what we really want to do, and why we do these kind of things. So, for instance, if you look at construction materials, like a concrete wall, for instance, at the macro scale, it looks like something very homogeneous. But if you look more into the details, you can see at the mesoscale, it's more like, well, there are different phases. They interact together. They have different compositions. And if you go even deeper in these phases, you have atoms and you have molecules. And these molecules, they have also different shapes, different kind of interactions. They can have interactions with ions and with water, many different things. So our idea is that we want to try to understand what's happened at the molecular scale and how it can affect the mesoscale and the macro scale. So the thing is, for instance, if you want to understand like the formation of a crack, well, maybe the origin of the formation of this crack is the formation of a gel that could be formed in the porosity of the cement. And in that case, that means the gel is important to understand how it forms, how it interacts with the cement paste. And if you want to understand this, that means you have to understand the chemistry. So the gel formation, for instance, is a reaction of several chemical reactions that makes the gel to form. So our problem is how we reach this molecular scale. So if you want to do it experimentally, because it's such a small scale and you're looking at amorphous systems that are non-crystalline, it's not very easy to have exactly the position of the atoms. But you can have information on clusters, for instance, the size of the grains. You can have information on the surface morphology, or you can also have information on porosity. That is also very important to understand what is the size of the pores, how they are connected. And this is helpful also for us to make the simulations. But one other thing we can do is a simulation approach. So the idea of the simulation approach is basically to do molecular dynamics. And by its name, molecular dynamics, of course, is very good at the molecular level. But our problem now for us is to try to reach larger scales, because we have a very good description of chemical reactions of very small systems. But if we are interested in cement, for instance, or a nanoporous carbon, we have to take into account pores. And let's say you have a pore of 1 nanometer. That means your simulation cell will be at least 3-4 nanometers in every direction. And so that means you will have tens of thousands of atoms in the system. And for us, this means the computation will be more and more and more expensive. So basically what's expensive in simulation is the cost of the forces calculation. So you can have different kind of approaches. You can have a very fine quantum approach where you will be able to look at, for instance, a chemical reaction in a small molecule or in a small system. Or you can do classical approaches that are basically trying to mimic the quantum results. And in that case, you'll be able to do bigger systems because the cost of the simulation of the force is lower. And there is another important factor for us is also the fact that we can do or we can't do chemical reactions depending on the methods. So basically, if you are interested in the formation of gels, in the durability of materials like cements, you have to take into account the chemical reactivity because reactions are making the system evolve in time. And so in our approaches, we use classical approach to have large enough systems. And we have to take into account the chemical reactivity, which is also a bit costly. So we can do systems of about 10,000 atoms to maybe 1 million maximum. Then after it's a bit too expensive. But it's already a pretty good size. So the idea is we try to increase the size of the system, as I've said before, but something even more important is to do long simulation times. So by long simulation time, what I mean is that we want to see a lot of chemical reactions because, okay, we have a method to mimic the chemical reactions, our classical approach. But if we do classical molecular dynamics, these events are most of the time too rare to be observed. So we will never have any chemical reaction. So what's the point of doing chemical reactive molecular dynamics? So what we try to do is we try to enhance the passage of the high energy barriers so that we can see evolution in time, basically. So now let's move to the supercapacitors and the porous carbons. So why we are studying these kind of materials is mostly coming from the work of Katerina and Roland and others when they were at MIT and now, where they've done some mix of carbon and cement and shown that it can be conductive. And so if you have a conductive material, that means you could make a capacitive system with this conductive cement. So what's a capacitive system? It's a system where you have two electrodes, an anode and a cathode, that are separated by an electrolyte, so it can be a solution. And if you apply a voltage on these electrodes, you'll be able to attract the charges on the two sides, the two electrodes, depending on their sign. And if you remove the voltage, you can recover the energy because the ions will be desorbed out of the anode and of the cathode. And so that you could do a kind of like a capacitor with cement. But if you think about simulations, you can't really, for now at least, do the whole system with cement and carbon and all the ions and everything. So what we do instead is we are looking at more simple systems where we have this structure here. So we have one porous electrode here of carbon and another one here, and they are separated by the electrolyte solution, which is water with chloride and sodium. And we have to apply a voltage on this simulation cell to mimic the adsorption process. We want to simulate the adsorption process. So this is also a challenge because there is no real easy way of applying a voltage at the atomic scale, and it's not very easy to do. And for instance, if we try to use the two most used methods in the literature, which is constant voltage and constant charge approaches, we obtain quite bad results. So basically, the constant voltage approach is a method where the atoms of each of the electrode will have an excess charge that will be added. And this excess charge is not constant, but it's modified so that the voltage is constant. That means all the atoms of the electrode will always feel the same Coulombic interactions. And if we do this, what we observe is that the charges, they can diffuse in the system, they can change. And we observe they diffuse to the external surfaces of the electrodes. And because of this, all the ions, they are absorbed at the external surface of the electrode, and they are not absorbed inside the electrode, which is not something very realistic. If we use the constant charge, the idea is opposite. Instead of fixing the voltage, you fix the charges. So you put an excess charge on the electrodes that is homogeneous and constant. And basically, that's what is represented here. So the charge is the same on all the electrodes. And the problem we have here when we do the simulation is we observe that the ions, okay, they go inside the electrode, but they go all in the middle, in the center of the electrode. And the reason is that's the place where the field is the strongest for the attraction of the ions. But this is also not very realistic at all. So if we look at our systems, actually what we have is something that has a lot of pores because it's a nanoporous carbon. And we have a lot of pores that are below 1 nanometer range. And if you think about it, a pore, what will it make to the structure? It will make defects. So imagine you have a very perfect crystal, like a graphite structure of carbon, and you punch a hole in the middle. Then around this hole, you will have a lot of termination of carbon bonds that are defects. They are defective structures. And this is something that is not taken into account in the other methods. So if you look a bit at the literature, for instance, on graphene and especially on graphene flakes, so if you have a perfect layer of graphene, all the charges are the same. If you have a flake like this, which is a piece of graphene, you see here on the edges, you have a lot of charges. So the charges localize on the edge of the flake, which is also the site of the defects. And if you put an atom on the top of the graphene layer, you observe that you also have a localization of the charges near the defects. So what does it tell? It tells us that charges should be located where we have defects. And this is what we've tried to implement in our model for the adsorption of ions. So we looked at how the chemical defects could be taken into account to apply the excess charge to adsorb the ions. So this is our structure and how we find the defects in this structure. Well, we took a very simple approach. We considered that if you have a perfect layer of graphene, this is a kind of hybridization of carbon that we call sp2. So not entering into the detail, but the angle between carbon-carbon-carbon atoms is 120 degrees. So in our system, we have about 70% of carbon atoms that are in this configuration, but we have 30% of atoms that are not in these configurations. And so what we calculate basically is this angle here between the carbon atoms. And the further away you are from 120, the higher will be the charge that we add to this atom. So this is a way of taking into account the chemistry of the system. And if you do it, the good news is that you have ions that are adsorbed inside the electrode, in the porosity everywhere, and at the external surface of the electrode. So this is what we see here. And now we can look at what's the dynamic of the ions, how many ions are attracted and adsorbed in the porosity. We can do a dynamics like this. And for instance, if we change the voltage, here we have a curve of the number of adsorbed ions versus the voltage. We see that sometimes at low voltage, we will not have the same number of ions adsorbed of chloride and sodium. And also sometimes you will have more ions adsorbed at the external surface or inside the porosity. So it depends a lot on the voltage. And you see here on the video, you can see that here it was a chloride. It's attracted by the red spheres here, and the red spheres are basically the most charged, the most defective carbon atoms in the structure. So there are a few information that we found with these kind of simulations. The first one, I think, which is very interesting, is that we observe that there is an asymmetrical docking at every voltage. So what it means that the chloride and the sodium, they don't adsorb in the same quantity in the two electrodes. And why is that? You remember the porosity? I've shown you the curve of the porosity. We have a lot of porosity below 1 nanometer. If you have one ion in a solution, it's actually not just an ion in solution. It's an ion plus a hydration shell because it's highly hydrated, it's solvated in the solution. And so if you adsorb this ion in the electrode, that means either you have to carry the whole hydration shell or you have to get rid of the hydration shell. And here our pores are too narrow to accept an ion and water molecules. The maximum we can have is 1 water molecule. So in the end, what we observe is an effect of how tightly the ion is bonded to its hydration shell. So for instance, at low voltage, we observe that very little sodium is adsorbed. And the reason is it's very tightly adsorbed attracted with the water molecule of the hydration shell. So this is because this is why we have the asymmetrical docking of the ions. And we also observe that when we do the desorption, some of the ions, they are actually trapped completely in the electrode and they don't go out in the simulation time. Okay, so this was what we've shown in 2022, and say maybe it's so 2022. Now we are going further. So now we are using a method that enables you to have at the same time the voltage, it's in a constant voltage approach, and to apply reactive force fields. So you can have chemical reactions in your system. So it opens a lot of new areas for us because we can do many new things. And a good thing is if you look at this picture here, this is the charge, for instance, for the plus electrode. So you see in red, the plus charges, in blue, the minus charges. And you see in the plus electrode, you have minus charges as well. So it's very heterogeneous. And this is what we proposed in the chemically driven charge localization approach, is that there should be a lot of heterogeneity. And we see that the charges, they localize on the defects, which is good news. And also on the external surface, because the external surface is a defect. And okay, so now we can do many different things. We can do flexibility, because actually a main limitation of what we were doing before is that all the carbon atoms were completely fixed, completely rigid. And okay, it may appear that the dynamics of carbon here is not so excessive, like it's not moving that much. But actually, when we do the dynamics with the rigidity or with the flexibility, we observe very different results in the adsorption properties, in the dynamics of the ions. So we believe it's something important to take into account, even if it doesn't appear very important on the videos here. We can also look at different kind of ions. So this is kind of the following of the story I was telling you for the asymmetrical docking. So now we can look at sodium, potassium, cesium, or other kind of alkali. Maybe we can look at calcium or other ions. And maybe the most exciting, we can do chemical reactions. So if we can do chemical reactions, for instance, here is the O2 splitting. We can look at the durability of the electrode, because the carbon atoms, they can break their bonds. We can look at the water splitting due to carbon electrodes, so with capacitive electrodes. And we can also look at desalination. So there are many new things that we are interested in now, and that we can now do with these simulations. So that's all I wanted to show you today. I'm pretty sure that you are not specialists of molecular dynamics or anything like this, so feel free to ask any question. And well, I would be pleased to answer.
Thank you, Romain. So we need to have questions about molecular dynamics. Guys, tell me that you're interested in molecular dynamics simulation. Omar, you have a question, of course.
Thank you for your presentation. So I just have a question about the graphene structure you are using. Are you using perfect structure of the graphene, or if you are using a kind of defect, this defect you are building by artificial building or something coming from experimental results?
So yeah, so we have different kind of structures, but the structure we use, like these porous electrodes, they are made by a reverse Monte Carlo approach. And well, the idea is to try to have the correct porosity compared to the experiment, and to have the correct radial distribution functions as well.
Okay, so you are building the defect in the graphene using Monte Carlo?
Yes.
Okay.
I mean, they are not directly put in the inside, but they are in the pair distribution functions.
Yes, I understood this, but I think my question here, it's regarding the density of defect in a specific structure. Are you comparing this for something coming from the experimental, or you're only testing the effect of the defect on adsorption?
Actually, and that's a very important question, I think. So now we have our model, the first one we used. I think it doesn't have that many defects actually in the structure, but now we want to try different structures, different model structure we have. So I think that's something that will play a big role. And another role that will be important is the chemistry, because you can have, when you have defects here, you can have terminations that are carbon terminations that can react with water. So it can make OH groups, or it can make COH or CH, or things like this. And that might play a very big role in the adsorption of the ions also.
Okay.
This we don't really take into account yet, but we will try to understand more.
Okay, so I just have also one question. If you maybe was able to specifying that a specific kind of defect would be very good for the supercapacitor or the application you are studying, there is a kind how we can move, so how we can create this defect in reality in a real graphene?
Yeah.
Oh, they are there actually. I mean, not in graphene. Graphene is per definition very sp2 carbons with no atom of chemistry, but those porous carbons. I mean, what's the percentage of sp2 in there? 90%?
72.
Oh, yeah, with the surface, yes. 70% with the surface.
Yeah.
These are just non-sp2 carbons, still carbon-carbon bonds, but not sp2. These are, how to say, geometry defects or topological defects. And then this is what Romain was saying, there you have all the rest of the chemistry. And in both cases, the chemistry and the geometrical defect, they localize electrons. So that's why you see the ions getting in the pore. And if you speak about supercapacitor, the difference with the capacitor, the super, is the fact that the ion can get in the pore. If the gas in the pore is because of a defect.
Yes.
But the question is, if you have too many defects, then you make the carbon not to conduct electricity.
Yes. Yes.
Then it's not an electrode anymore.
Yeah.
So there is a trade-off between the amount of chemistry or defect you want to still and to help the ion getting in the pores. But too many defects means that you're killing the conductivity.
Thank you. To answer the question, I don't think experimentally you can control exactly what kind of defect you will have.
But you can measure it.
But
you can measure it.
Yeah,
there are different ways to test that.
For the graphene, you can control the defect because as I understand from the literature that how people create defect in graphene by irradiate the graphene structure. So you have the graphene and start irradiate by the gamma ray, and then you can control the defect.
Yes.
Okay. Thank you.
Thank
you for.
Yes, Mustafa.
Very nice talk. Thank you so much. I just I'm curious if you tried to test the variation of the pore thickness itself. So at the same voltage, so you don't change the voltage, but you change the pore thickness, because that would change the electric field between these two electrodes, and it would actually lead to interesting phenomena, especially as your pore size gets thinner and thinner and thinner. Have you tried testing this?
We haven't tried, but yeah, it's definitely something we want to do. But now, basically, we thought that maybe these models are a bit too complex, so we want to try to do graphite or graphene with different distances and try to see what happens, and have more control on the defects. Like if we put one defect, what happens basically? So yes, that's a very good idea.
But the effect, yeah.
Separation,
Yeah, the separation between the layer, yeah.
But you do have a double layer of ion on the outside. So you have some ion getting in the pores, but most of them are on the outside. You have a double layer, like, usually the air. And when you calculated the Dupuis length, it comes to the 2-3 angstrom that you will expect with this kind of ion concentration.
The separation is
around 30 angstroms, something like this, 30, 40.
40 angstrom, yeah, 4 nanometers.
I think it's important to try different spacing, also for looking at kind of confinement effect maybe, or something like this. Yeah, could be nice.
Yeah, I'm just curious. So you said it's 4 nanometer, and how much is the voltage?
The voltage, we go from 0 to 4 volts.
4 voltage is the maximum.
Yeah, but this is not the voltage with respect to the reference electrode.
Yeah.
Because we have 2 carbon electrodes.
So it's the voltage difference.
Yes, between the 2 carbon electrodes.
4 volts.
Yeah, but the 4 volts will correspond to the 1.2 almost for the water splitting with respect to the hydrogen reference electrode.
Right.
This is the 1.2 thing is with respect to this reference electrode.
Right.
There's 4 volts for the 2 carbon electrode will be that condition. So we are not yet splitting the water in this case.
In experiments, basically, they do have one electrode and then the other one is not in the same bath. So yeah.
Thank you.
Any other questions, simulation guys? No? Thank you, Romain.
Yes, please. Romain, can I?
Yes. Who is sleeping over there?
Edo speaking.
No, it's okay to wake you up.
No, it's all right now.
All right now.
So I'm very sorry I can't attend the meeting. It's I've been following it. It's great. So I've got a Romain, fantastic talk. Thank you very much. I've got just one question, two, in fact. Can you go maybe back to the slide of your different ions in your system and the different behaviors they display? There was one slide you had about this, I think.
Yes, here.
That's the one. Yes. So are you saying you can now start to play games with different ion compositions because different ions have different strengths of water shell formation, I guess. So it's easier for some ions to shed the water shell than for others.
That's one thing, yes. The other thing is the size of the ion. Like if you go to larger ions, basically they will have a looser hydration shell, but maybe they big to enter in the pore. So maybe there's a kind of trade-off.
Yes. Have you considered the case of lithium here? Because of course that's the smallest one, but it's the strongest hydration shell.
I have not understood the question.
Have you considered the case of lithium ions?
We haven't tried yet, but yeah, it's very small, so it could be interesting to look at.
It's got a very strong hydration shell, yeah. So it's more difficult to shed that shell.
If I recall correctly, it has a strong hydration shell, but it's exchanging a lot the water molecules around. So
Okay.
maybe it will have
Right.
behavior.
Okay. Great. I'd like to talk to you in more detail about this. Great stuff. Thank you.
This is one thing that the cesium for me was a surprise because it is a big ion. So yes, the hydration shell is loose, so easy to dehydrate. But for me, it was not going to enter. In the simulation, it enters the pores, right, Romain? It's because of the flexibility of the electrode. The carbon-carbon bonds are accommodate. Because if you do a frozen electrode, then you don't see the cesium getting in the pores.
Okay. Can I ask maybe one further question? How important is it to get the pore size distribution right? How does the penetration behavior depend on the right sort of combination of pore sizes?
So I understood the first part. The pore size distribution, it's I think it's calculated from growing spheres in the porosity.
Right.
No, I think I was asking how important is, right?
Exactly.
Yeah.
Exactly.
I remember.
Yeah. I think the point is that we have checked only this pore size distribution.
Yes.
We don't know if we change it, how it's going to change the results. I don't know if this is what you're asking, Edo.
Exactly. That's what I'm asking. And is there space, let's say, for a design, an optimal design of a carbon with an optimal pore size distribution to facilitate transport?
Yeah, you're right.
Right.
From other works, from this carbon from carbide, CDCs, the work of Mathieu Salan and Benjamin Rothenberg in Paris. They were showing that so the carbon, they have the pore distribution is shifted towards larger pores. And in those pores, they do see pair of plus minus ions together.
Right.
Which we don't see in those pores that are like less than 1 nanometer. Basically, the ion, when they, in Romain simulation, when they get into the pore, they are basically naked.
Yes.
And
so that's very different, yeah? You found it very different behavior.
Yeah, that's one thing we have to try as well. This pore size, the chemistry, and
Great stuff. Yeah,
okay.
Thank you.
Thank you. Any more online or in for real questions? Right. Thank you, Romain.
thank you very much.